So today's topic is self-induction. This is a continuation of EMI. So many of the concepts involved are same as what you have in case of EMI. So let's consider a solenoid. A typical solenoid, let the radius be R, the total number of turns are N, and length is L. And see, many times we are more concerned about number of turns per unit length. So the small n in a normal convention what you use will be total number of turns divided by length of the solenoid. So this is a solenoid here, and if this solenoid, if current flows in the solenoid, so what would current in the solenoid will lead to? The current in the solenoid will create field, and field will create flux. So if there is a current in the solenoid, the current in the solenoid itself creates flux in the solenoid. So what will the flux of, in this case, typically what we do, we know that field is uniform only in the central portion of the solenoid. What is the central portion? We don't define it very specifically, but except for the end region, the field is constant all across the interior volume of the solenoid. So what we consider here, even for end region also, we assume this end part is small. It is a long solenoid. We assume the field to be constant and uniform, field to be uniform all across the volume of solenoid. All through the length of the solenoid, field is considered to be constant. Okay, that's an approximation. Assuming that length is much longer and length is small. So what would be flux in that case through the solenoid? So okay, that is also is not too difficult. Flux would be each coil, the field is perpendicular to the cross section of the coil. So flux through each coil will be into area of the coil into B. And since the total number of turns are N, so total flux through all the coils put together is N times BA, which is nothing but number of turns multiplied by flux through each coil. That is NBA. This term is flux through each coil, and this total number of turns. We can express in terms of these parameters. So what is N here? Total number of turns. Total number of turns we can express in terms of number of turns per unit length into total length. So this we expressed it like this. What is value of magnetic field is mu naught Ni, and area of cross section is A. So for the let's leave it A. And if I bring these two things together, what is L and A? We can write it in a number of ways. This expression is easy. We can easily write this expression of flux, and this term we can write in a number of ways. I have written in one particular way. What we have done, we have taken length into area of cross section of the solenoid, and this is the length of the solenoid. They have written in terms of volume. So what is flux? So the flux is equal to mu naught N square volume into current. Okay, and you notice here, this is flux. So what we notice here, the flux is, whether if an entire thing can be taken for a given solenoid, I can take this whole thing as a constant. So what is flux is equal to some constant into I, or flux is proportional to I. Is this something unique to a solenoid? Actually, if we take any coil of any shape, since the field is proportional to I, the flux also will always come proportional to I. So in this case, this is how it is. Flux is proportional to I. In solenoid, it's very clearly we can see, but it is also true for other coils, any other shape. And so what will happen if I vary this current I? And we know how the current can be varied. Suppose the current is connected to battery, and maybe there's some variable resistance here. If we change the resistance, current can be varied. What will happen if the current is varied? Based on what we already know. And this is not a too difficult question to answer. If current is varied, since there's a flux associated, if current varies here, the flux also will vary. The flux is a function of current in the solenoid. So as the current in the solenoid is varied, the flux will vary. If flux changes, it will lead to induced EMF. So what happens here? As per Faraday law, there will be induced EMF in the coil. And this phenomena is called self-induction. What is causing induced EMF in a coil? Due to change in the current in the coil itself. So as the current in the coil varies, it induces EMF in the same coil. So earlier we have seen some cases where there are two coils involved. In case of self-induction, there's only one coil, and it leads to this. Any circuit will have this phenomena, not only in case of a solenoid. Any circuit will have this kind of phenomena. So suppose we take a circuit like this. This is a common way we draw a circuit. And here also we close. As the current flows here, we know this, if the current is flowing like this, it will create field. So if we take this area bound by this particular loop here, it is forming a loop. Any current will form a loop, any current circuit will form a loop. And there's a magnetic field all through this area, and hence there's a flux. But in this case, what will happen? The flux would be smaller than the relative terms compared to flux being created in a solenoid. But it's true for every case. Here, flux is maybe more intense, the magnitude is more. And second thing here, flux can easily be calculated. Other problem, what we notice here, flux may be smaller. So this phenomena of self-induction is more pronounced in this case, more noticeable, of higher magnitude. In this coil, it is of lesser magnitude, less noticeable. But nonetheless, this phenomena exists in all loops. And whenever the current is varied, we'll have change in current will lead to change in flux, will lead to induced EMF. And what is induced EMF? It will behave as if the circuit has additional battery. That we know already, and it will behave like as if there's battery in the circuit, and EMF of the battery will be equal to d phi by dt. Okay, so we'll continue further. So as the field is proportional to current, the flux of the loop will be proportional, not only in case of solenoid, other cases. So we can write something like this. So what is L here? L is the constant of proportion. Phi is equal to L times I. And this term, the constant of proportion, is called self-inductance, self-induction, or sometimes we also use coefficient of self-induction. That's L. And what does this L depends on? And again, if we go through very easily, you can notice in previous term, we have written as mu naught n square into volume. It depends on the geometry. So as long as any coil is there, if we do not disturb its shape, its geometry is not altered, its self-inductance or coefficient of self-induction also remain constant. It depends on geometry. And how else we can define this term L here? This is a term typically use this notation capital L. It is equal to flux through the loop when unit current flows through the loop. So that's another way to understand. How do I calculate self-induction here, a coefficient of self-induction? So coefficient of self-induction is equal to flux through this loop when a unit current flows. So this is equal to phi when current is equal to I. Or so what would the unit of this term L? L unit will be same as unit of phi divided by I. What is unit of phi? Flux unit is Weber. And Weber we divide by ampere. Weber by ampere. So what happens if we divide ampere by Weber by ampere? It comes into a new person. So what is a new person here? New scientist is Henry. That's a unit for coefficient of self-induction. So typically what he had done, and how would he calculate L for, and what are the things required to calculate this value of self-induction? So any coil, what he had done, similar to what he had done in case of solenoid, let the current through coil be I. So for a given current I, if we can calculate field at all parts of the area bound by the coil, then we can calculate flux. What is necessary to calculate flux? We should be able to calculate the field. If we can calculate field, then only flux can be calculated. So when we calculate flux, and flux is phi, L is equal to flux per unit current. That's what flux is. So that's coefficient of self-induction is. And that's the method. So let's come back again. So what is flux equal to NBA? This is what we had done in case of solenoid. We are back to, so again, we are just looking at, we have just rewritten what we have calculated in previous slide. This is what we have done in case of solenoid. In case of solenoid, it is possible to calculate flux. All through the cross section of the solenoid, field is uniform. It becomes easy. Any other shape, it won't be so easy. So this is what the term is. So if this is what the equation we have, can we calculate value of L here? Pretty simple. This is the term which is a constant. This is value of L here, phi by I. And again, if you look at this, you notice what is the n square term. N square also depends on the geometry, how the coil has been wound, what length of the solenoid, and volume depends on what is the cross section area, length. So it depends on the geometry of the coil. And until we change the geometry, L will remain constant. So in this case for solenoid, what is L equal to? Coefficient of self-induction in case of solenoid is mu naught times n square into volume of a solenoid. We can write in different forms. The volume can be written in different forms. Of you can, if solenoid has circular radius of r, we can rewrite in other terms. But I think this term is easier to remember, so I prefer this term. We can write in other forms as well. Just have recap what we did here. So in a coil, if the current I flows, what does current lead to? Current leads to magnetic field. And magnetic field creates flux. So what we have done here, in case of coil, we have written the flux in another form, and this flux is proportional to I. We have written flux as equal to L into I. So for a given shape, L is a constant, and we'll see later L can be determined even experimentally. So for a given coil, if L is known, then for a given if current is known, if we know what is the current flowing through the coil, we can easily calculate flux. So this is another way to calculate flux. And if we know the value of coefficient of self-induction, so phi is equal to Li. That's the new thing we have learned. Phi is equal to Li. That's the new term. Phi is equal to Li. Phi is equal to Li. Coefficient self-induction to current. So what is EMF here? Still Faraday's law is valid. So EMF is equal to d phi by dt. And I'm just writing the magnitude. We'll find the direction using Lenz's law. So, and we put this values here. L is a constant. It becomes L into di by dt. And if average EMF you have to calculate, it becomes delta I by delta t. So, so what we understand from this equation, whenever any coil acts like a battery, if current through it varies. So it will act as battery only when the current is varying. It will behave as if it may have an additional battery. In addition to this battery, if the current is constant, it will just behave like a resistor. It will not have any battery kind of behavior. But moment we vary the current flowing in the circuit, or we make an effort to change the current in the circuit, it will start exhibiting battery property. What will the EMF of the battery? Very simple. EMF of the battery will be L times rate at which current is being varied, L into di by dt. So we'll see what the direction of EMF will be. Let's understand in this case how would EMF act, which direction would act. We understood if L is known, if rate of change of current is known, I can calculate magnitude of EMF. Now we look at which direction. The direction will come from Lenz's law. So let's see in this is a circuit here. So in resistance, this is how we show an inductor. Any coil will have inductance. Only thing, in case of solenoid, value of L is higher. And the shape what we use for inductor is same as a solenoid shape. This is a typical convention. So this is one current element, this is second current element. And this is the first time we are using an inductor in a circuit. What kind of circuit? DC circuit connected to a battery. So let's see, there's a key here. At t is equal to time t is equal to 0, we press this key. So until now the current was not. So before the key was pressed, current was 0. What is the effect of pressing the key? See, if the inductor was not there, our understanding so far was if the battery EMF is E and resistance to effective resistance of the circuit is R, there will be steady current I is equal to E by R. So if we do not know anything about L, we would have thought that as soon as we close the switch, in almost instantaneously, current will rise to E by R. So sudden change from 0 to E by R. So this is something, so what it understand, if we normal understanding, it will lead to sudden change in current. So if more sudden the change in current is, higher is di by dt. So if current was, if L was not there, the current would have grown instantaneously to E by R from 0. So there's a moment we press the key, what we understand as far as L is concerned, there is a change in current. Current is trying to increase or decrease. There's a change, there's an increase in current. So as the current grows, flux will change and it will induce EMF. And how it will rise, since the current is trying to grow, that's a cause which is inducing EMF. So EMF will oppose the growth. How would EMF oppose the growth here? So what is happening? The current is flowing in this direction and tending to grow. So it will create an EMF which will oppose the growth. What will be the polarity of EMF induced? EMF induced will be opposite to direction of current. It will try to induce current opposite to direction of growing current. That will be how this will be. So if inductance, so that's what inductance, it does not allow current to instantaneously increase from 0 to E by R. It will slow down the process. It opposes the growth of current by inducing an EMF. Lenz's law. Okay, that's what it is. And what is the direction of induced EMF? Is opposite to current. And what will happen? So suppose we keep this keep the key closed for a long time, and the current I is flowing. Suddenly open the key. Opening the key also will amount to sudden change in current from I value to 0 value. Actually, if you open the key very quickly, and it will immediately current will drop to 0. That's what the current will happen. So current drops almost instantaneously to 0. So one more thing we see later also, whenever we open the key, the rate of change of current becomes very large if you open it quickly. So di by dt is large, induced EMF also is very large. And which direction? Now what is happening? This is the direction of current, but this current is tending to decrease suddenly. How would it oppose the decrease? By inducing a current in the same direction. How does it induce current in the same direction? By creating EMF which supports the direction of flow of current. So here, when current is increasing, opposite to direction of current. When current is decreasing, in the same direction as direction of current. So EMF, in this case, in the same direction. So, in summary, what we can understand, inductor opposes the change in current. Okay, that's it. So this is something like not electric, sorry, this electric inertia. It acts like an electric inertia. Something like mass. Mass, what does it tend to do? Mass opposes change in velocity. Okay, it doesn't allow velocity to change suddenly. If mass was 0, velocity can be changed almost instantaneously. But because of presence of mass, however large a force you will apply, change in velocity will not be instantaneous. Similar way, this also acts as an electric inertia. Okay, and just to again in terms of figure, if I is increasing, opposite, Lenz's law. If I is decreasing, same direction, again Lenz's law. And how much EMF will be? If we know the value of L based on the geometry, how do we calculate again L? So again to recap, how to calculate L? If current I is flowing, it creates magnetic field. I calculate flux through the coil through multiple loops through all the loops here. If I calculate flux, divide flux by current, or flux per unit current is equal to L. If I know the value of L for a particular coil here, I can calculate EMF if rate of change of current is low. So instantaneous EMF is equal to L times di by dt. Polarity is given in this fashion. Polarity is given by Lenz's law. How would orientation of the battery will be? It will depend on whether I is tending to increase or I is tending to decrease. Increasing, opposite direction, decreasing, same direction. Let's understand a little more. So what we understood, the current will not go instantaneously. Now the question comes, how long will it take? So again, I forgot one more point I will add here. So suppose this inductor and this resistance also, to better understand, to visualize what is happening. This resistance we can view as like a bulb. So there's a bulb here. So what will happen as the brightness of the bulb depends on the current flowing through it, I square R. So it will vary as square of the current which flows through the bulb. So if if this inductor was not there, as soon as you press the key, immediately the bulb will achieve its maximum brightness. Of course, we are not talking about variation of resistance remaining constant. But because of presence of inductor here, it will oppose sudden increase in current. So it will oppose sudden growth of brightness also. So what will happen in this case, because of presence of inductor, it will achieve its brightness over a period of time slowly. And in this case, what will happen? In this case, when the current was flowing, it has certain brightness. Moment I open the switch here, the current will tend to drop suddenly. It will induce a large EMF which is support the current here. And if we open the switch suddenly, what we'll notice here, the brightness of bulb actually increase. Can you think of reason why the brightness of bulb will increase? Because it will behave as if it is connected to a battery of large EMF. If rate of change of current is large, which is the case when we suddenly open the switch. When it suddenly opens, suddenly the current drops in the circuit. So there's no current created by this battery. So this battery induced EMF will create current. This will create an EMF, and we'll find for a very brief period, this bulb will shine very brightly. That's what happens because of the induction effect. Now, what time it takes, how the current will go, similar to what we had done in case of RC circuit. RC circuit, we had a resistance and we had a capacitor. Our understanding was if in batteries connected to capacitor, Capacitors acquires the same potential difference as the battery. But because of presence of resistance, it doesn't happen immediately. It takes some time. Something similar happens here also. Let's take LR circuit, which is an inductor and a resistance, and we take the charging kind of circuit. Charging means where the current is increasing. So there's a switch here. We close the switch at time t is equal to 0. So let the switch be closed at time t is equal to 0. And this derivation is very similar to what we had in case of RC circuit. So if you recall in RC circuit, we'll do something similar here. So let's take the current also. We don't know if this is something, we don't know how the current will go. So let's assume at certain random time t, let the current be I. The current here is I, and rate, and at this instance, the current rate of change of current is di by dt. This I is the current, so at a particular time, and di by dt is the rate at which the current is changing. Okay, so what did we do? How did we form an equation in case of RC circuit? Using Kirchhoff loop rule. At a given instance, something similar we'll do here. So here also what will happen, this inductor will act as a battery. And what is the battery? This induced EMF, this induced EMF. Which direction? It will act in the backward direction. If I apply Kirchhoff loop rule, it will come like this. This EM, this will be from here to here increase E, and this will be equal to minus IR. E will be equal to, either I could have written minus IR minus L di by dt is equal to 0. I have taken IR and L di by dt to other side. So this EMF will be equal to the drop across inductor and the potential drop across resistance. And here, what is the EMF potential drop here? It is like a battery. So if I go, it will be from positive to negative. How much this EMF is? L di by dt. And this is IR. So this equation, and this equation, it has two terms which are varying, are current and time. So I can solve this differential equation for current and time by integration. Very similar to, again, RC circuit. So what we do here, then again, if we take, let's take this term. So E minus, how do we rearrange this term here? This term, I could have written one more step. E minus IR is equal to L di by dt. Okay, or dt is equal to this expression. We get this expression. Now there's the so both variables are separated here. I can easily integrate this point. So here with both can be integrated. If I integrate from here 0 to t, and corresponding value current at time 0, which was 0, and plus the current at time t is equal to I. If I integrate, this comes in equal to t, and this integration, the coefficient of I is equal to minus r. So which gets divided by L divided by minus r into log of this term, E minus IR, and these are the limits 0 to I. And when I substitute here, okay, and again here also we take L by R is equal to tau. This see, whatever dimensions we have on the left hand side, right side also have same dimension. This is log term, it will be dimensionless. So dimension of t is equal to same as dimension of L by R. So I could have written, so this term I could have, yeah, one more step we want to write. We can write what is this term equal to. This is equal to, in place of L by R, I am writing tau. Tau into log to the base E minus IR. So I take this minus tau to other side, it becomes t by minus t by tau, negative sign, and this is log of E by R, sorry, it will come into minus log of, and we substitute 0 here, in place I, it becomes equal to, you can say log to the base E, and this expression. So this is what we get, t by minus t by tau, and we realize this term, we had done it before, and it's not very complicated, and we get I is equal to E by R, 1 minus E raised to power minus t by tau. And by now we are little more familiar with this expression, and if you recall, we had a similar expression, but in case of I, there was Q, and this expression was slightly different, but rest of things are, overall behavior is similar. If you try to recall, in case of RC circuit, charge at any particular time Q was equal to CV into 1 minus E raised to power minus t by tau. And here that we obtain the expression for charge, here we obtain the expression for current. This is how the current will vary. And whatever graph we had between Q and T, same nature of graph will be have between I and T. So basically both the nature is same. So Q is replaced with I here. So if we recall what happens in case of RC circuit, it's easy to understand how the current will vary with time in case of LR circuit. Okay. Okay, so that's the formula, and we'll come to that formula again. And just to understand a little more. So as we have seen in case of RC circuit also, there's charging state and there's a discharging state. So let's look at this circuit we have. This battery is connected. So how do we charge it? What should be the arrangement? Can we think of this three-way switch? If I want to charge, basically I want to current to flow. So charging this battery is part of the circuit. So if I connect S to A, if S and A are connected, it will lead to charging. And after we achieve a steady state, if I suddenly switch from S to B, what will happen? The battery will go out of the circuit. Battery will not part of the loop anymore. It will become only L and R are connected. It's similar to what you have in RC circuit when charged capacitor is connected to resistor. Here what will happen when you switch from A to B? It is current carrying inductor is connected to a resistance, and this will be discharging. Current will drop. This is discharging. Discharging is when battery is connected, and discharging when battery is not connected, and inductor having initial current. Let's look at the charging here. Charging, this is the value of this is expression we obtained last time. So when we have understood that, we have seen it before. What will the value of current at time is equal to after a long time? What will the current here? So this after a long time. What does after a long time means? This expression that t is tending to infinity. If t is tending to infinity, this expression could be also written as E by R 1 minus e raised to power, 1 by e raised to power t by tau. So t becomes infinity, this term also, this infinity, the denominator, this whole expression becomes 0. So when at a long time, when as t tends to infinity, the current is E by R. And which is not very surprising. After a long time, it behaves as if this inductor is not present, is like a conducting wire. Okay, so that's what happens after a long time. In case of charging, so initially, what is the initial current at time t is equal to 0? Initial current is 0. It is exactly reverse of what happens in case of current in LC circuit. So there, after long time, current becomes 0, and initially the current is E by R. So it is reverse here. Initially the inductor behave like an infinite resistor, open circuit. So at time t is equal to 0, soon after the switch is closed, soon after charging begins, it behaves like an infinite resistor, open circuit. So whenever we have to solve a question where t is equal to just soon after closing, any branch which contains inductor can be treated as an open circuit. And it's kind of revision. We have done something similar in case of RC circuit. What happens after a long time? Inductor behaves like a zero resistance. It's like shorting. So basically we can connect whichever branch or wherever there's an inductor, I can replace the inductor with a straight conducting wire of zero resistance. This is our understanding, and this equation leads to these two conclusions. Okay, this is not just something that has come out of nowhere. This is interpretation of this equation at time t is equal to 0 and after a long time. And if you plot the graph also, will come to same thing. And what at time t is equal to tau, what this expression is, we have seen it before. T is equal to tau, it becomes 1 by 1 minus 1 by e, which leads to I is equal to 0.63 I naught. What I'm using as I naught term here, I naught is maximum current or current after long time, which is equal to E by R. So it reaches 63% of its final current value in time is equal to tau, which is called time constant again. So earlier it was time constant for RC circuit. This is the time constant for LR circuit. And what is value of tau? There the tau was RC, here it is L by R. Remember that one? This is something you must memorize here. There's no choice here. And if we calculate the dimension will come to same dimension as time dimension. In case of discharging, what will happen? The battery will not there. We are not writing the expression. It's very similar to our circuit. Discharging, current will, see if the current was flowing, the current will decay exponentially. And this I naught indicates initial current. At time t is equal to 0, this is initial current. And in this case, current will decay exponentially, similar to decay of charge exponentially in case of RC circuit. And in this graph, I hope all of you should recall, if I plot I on y-axis, t on the x-axis, this graph is familiar with, and at time is equal to tau. If this is the maximum current, which is E by R, at time is equal to tau, it will be equal to 63% of the maximum value of current. And this is how the potential will be. The potential will drop exponentially. And actually, same curve will follow in case of discharging. Discharging current will be like this. And at time t is equal to tau, discharging current, if the initial current was I naught, after time t, during discharging state, current will be 37% of the initial value. So this is charging state, it reaches saturation current. At time soon after this switch is closed, or soon after the charging starts, current is 0, which in infinite resistance. And here, after long time, resistance offers close to 0 resistance. That's what we have written here. Initially, t is equal to 0 plus, behaves like an open circuit. And in case of after long time, it offers 0 resistance, just like a shorted branch. And this is okay. Let's try and understand what will happen in case of series combination. We'll not go into much of derivation, but let's get an understanding of what is happening here. And suppose in the same circuit here, this is two inductors were connected, L1 and L2. What would happen? What change will happen in my expression if I write Kirchhoff loop rule? Only thing what will happen, earlier there was one term, di by dt. Since they are part of the same, current is common, and hence current is common at all instances. Hence, di by dt has to be common across both. The rate and phase, this is a property of the circuit here, di by dt. So EMF induced here will be equal to L1 di by dt. EMF induced here will be L2 di by dt. So this would be my expression, and in this expression can be written as, I can combine those into one expression. So whenever we have something like this, actually it can be replaced. What is the equivalent L here? Equivalent L is L1 plus L2. I can this can be in place of L1 plus L2, I can replace L equivalent. I can use a single inductor. So what does this equation imply? This equation tells me if two inductors are connected in series, the equivalent inductance is equal to L1 plus L2, same as a resistance. So this behaves in a similar fashion as resistance. Only requirement is something I'll come to explain a little more in detail. What is necessary? They have to be at a far distance apart. Reason why they have to be far distance apart, because this is something this will create some field. Okay, so what should happen? The flux through L1 should be only due to current in L1, and flux in L2 should be only due to current in L2. It should not have any flux. L2 should not experience any flux due to L1, and L1 should not experience any flux due to L2. For that to happen, the distance has to be large, so that field in the area of the coil of second inductor due to first inductor is negligible. Okay, so as long as they are connected in series, not close to each other, I can replace them with one single inductor equal to L1 plus L2. So principle followed is similar to what we have in case of resistance, even at larger spacing. What happens in case of parallel combination? Again, I'm not going to too much of detail, but because the derivation is not required, it will behave parallel combination just like resistance. What is equivalent inductors? L1, L2 divided by L1 plus L2. And we normally don't come across many such applications. Important part, what we come across here, if this one is di1 by dt. Now, if they are connected in parallel, there are two independent branches. So the current values of rate at which the current grows or current changes need not be equal here. But what has to happen between 2 points? This induced EMF have to be equal. This path and this path, they are connected in parallel. That's a property. So induced EMF in 1 and L2 both have to be equal to each other. Or I can write L1 into di by dt is equal to L2 into di2 by dt. di1 by dt and di2 by dt. And if we integrate from 0 to t, initial current being 0, L1 at any instance, if this current is I1 here, and this current instantaneous current is I2, at any instance, L1 into I1 is equal to L2 into I2. That's the equation which follows in case of parallel circuit. So parallel combination, equivalent inductance, and this how the current would be at any instance when two inductors are connected in parallel. Okay. Now there are certain numericals we can solve based on the simple examples what we have dealt with. Only thing new what we have done something like this. If I had to just tell what is the new thing we have done, we have just done. We have written phi is equal to Li. And that tells me that EMF also, EMF is equal to what? Since EMF earlier we used to write as d phi by dt only in terms of magnitude, I can write on the same term. From this expression only, we get L into di by dt, that is instantaneous EMF. And if I have to write average EMF, it will be L into change in current by time. That's the only thing new I had done. And we have defined this term as coefficient of self-inductance. Or inductance, coefficient of self-inductance, inductor, they're all terms people use for the same term here. And this question is simple to solve. Let's look at this, what the question is. If an inductance coils, current increases from 0 to 6. What is given here? Delta I is given. In 0.3 seconds, delta T is given, which produces induced EMF of 60 volts. So this EMF induced also is given. What is EMF induced? Actually, this is average value, not instantaneous. What is the value of coefficient of self-induction of coil? It's a direct application of this formula. Average induced EMF is equal to L delta by dt. So very simply, you can substitute value. EMF induced is equal to 60 is equal to L. Here the sign is not important here. What is change in current? It changes from 0 to 6. The change in current is final current minus the initial current, which is 6 itself. And divided by the time it has taken, divided by time. That's all. And unit is Henry. So there are pretty simple questions based on this. Let's look and understand the next second question. Self-induction of a coil having 200 turns is 10 millihenry. What does this term indicate? Let's try and understand again. What does this term mean? So this term, if another way to understand, if in this particular coil, if we pass a current of 1 ampere, if the current is equal to 1 ampere, this coil will have a flux. All coils, all is coil turns put together, will have a flux equal to 10 milliweber. That's what this term means. I hope you understand here. What is L equal to? L is equal to flux per unit current. Or if this is given for any value of current, I know what the flux in the coil is. So that's again to kind of have a quick recap of what we have done. Here, what you need to do here, again, just to have a quick recap, what we have done here, in this case, only thing you are done, we have defined phi is equal to Li. And then based on that, we have one more way to define EMF, which is equal to LdI by dt. That's the only thing you have done so far. Let's apply the same thing again. Calculate the magnetic flux to the cross section of the coil corresponding to current of 4 milliamp. This is what we need to calculate for this given value of I. And L is given. So this is a direct substitution. So also determine the total flux. So for how would calculate the total flux here? Value of L, which is 10 millihenry. And current is equal to 4 milliampere. Okay. Thus, so many Weber is the flux through the whole coil. Okay. So also determine total flux will be the each turn. This is a flux through how many turns? 200 turns. And we are assuming in this case, it's a kind of solenoid or coil. Here we are ignoring any end effect or fringe effect. We assume that field is constant all through the length of the conductor in a coil, all through the cross section. So each coil will have equal flux. If this is flux for the entire coil, the flux for each turn will be equal to total flux divided by number of turns. So this will be equal to phi by n. How many turns? By 200. So this term I divide by 200. That's the flux per unit turn. Okay, so this is connected to a driver and drives a constant current. So this is something you have seen this earlier, something like this. So the switch is closed here. It is driving constant current here. And what is the constant current here? This R is given. What is the constant current? Is steady state after a long time. So when we talk about constant current, it's steady state current after a long time. And I think I hope you recall what is constant current will be equal to. Constant current will be equal to E by R. EMF of the battery divided by the resistance. This is the constant current which is flowing. So this will be equal to 2 amperes. So this current of 2 amperes is flowing at a particular instance of time. The switch is suddenly open. So sudden also, when we talk about sudden, it depends on how quick you are. And even though this never the time taken to open the switch is not 0, it has taken some finite time. It has taken 1 millisecond to open the switch. Calculate the induced EMF across the coil. So what is happening the moment you open the switch? The current will suddenly drop to 0. In what time? This is the time when it is open. It means that there's no current flowing in the loop. So what will happen? It will induce an EMF here. What is induced EMF? Again, there's nothing new. So induced EMF is pretty simple. EMF we used to write as d phi by dt. Now we write as phi is equal to Li, because L into delta I by delta t. Here also, it is not talking about instantaneous EMF, it's talking about average EMF, though it is not very specifically mentioned, but this is something we can easily infer. So let's put those values here. What will the induced EMF here? Thus induced EMF will be L is how much? N is 10 Henry, pretty large value actually. And what is delta I? The current will drop from where to where? Will drop, it was 2 ampere to 0. So change is actually 0 minus 2. Final value minus initial value, but we are only concerned with magnitude, doesn't matter. Change in current is equal to 2 only. And time taken is 1 millisecond, so 10 to the power minus 3. So what is this equal to? This is equal to 20 into 10 to the power 3 volts. So what you notice we change, it creates a battery, or it induces a huge EMF if it is opened suddenly, very large. Okay, and creates kind of spark and other things. So, and if you are a little slower, so EMF induced for what period? It is instant. Okay, this is for what period? For 1 millisecond. For 1 millisecond, if we assume the EMF almost to be constant for 1 millisecond, this is the, it will behave, coil will behave as if there's a battery of this particular EMF. But circuit is open. Okay, so what this battery will do is secondary thing. The circuit will be open, but it will be like a battery. And what is the polarity of the battery? This circuit will look like this. This part is open, but it will have this battery connected. So it will have two batteries. One is this and the one is this. And you notice here this EMF is much larger than the battery which is connected. So using this kind of arrangement, it is possible to create a large EMF, though for a very brief time period. But using an inductor, by sudden opening of switch or by suddenly making the current to drop to 0, it is possible to create a very large EMF for a very brief period of time. That's an important property of an inductor. Okay. Similar way, let's look at this. This is also a variation of the same question. An inductor of 5 Henry, but huge inductors, carries a steady current of 2 ohm. Very similar. How can a 50 volt self-induced EMF be made to appear? Now, if I want to make a particular average EMF appear, L is constant and delta is also. What we can do, we can control delta T. Depending on how much time do I take to open the switch. If I open it slowly, EMF developed will be smaller. If I open it very quickly as we have done here, the EMF will be larger. So in this case also very similar question. If I want EMF to be 50, it will be L, delta I will be equal to 2 ampere, and it depends on what time do I take. So I can choose the time to induce a particular average EMF. We can choose the time it takes to open the switch. By opening it very quickly, large EMF. By opening it slower, smaller EMF. Okay, so these are some key points related to self-induction. All of you just go through this carefully, see that everything is understood. If any part is not clear, again, I think tomorrow, next day, when I have this session, we can have a quick recap, or we can have quick clarification of doubts related to this. But this topic is essentially extension of the same thing what we had done. Very small new thing has been added, and if all of you have paid attention, this is very easy to understand. Okay, so that's where I'll end the session here, and any doubt we can deal with later. Thank you.